So now that we've talked a little bit about generalized linear models, as well as the logistic regression model, we're going to discuss how we would actually go about estimating the parameters. When I'm talking about estimating the parameters, in our specific situation thus far, we're going to be trying to estimate alpha and beta in our function. So again, we're going to have a random sample of n observations. Here, the values of y's are just going to be zeros and ones. And again, the reasoning behind that is zeros are going to represent failures and ones will represent successes. So thinking about our example, we're going to have a 0 if the kick was missed and a 1 if the kick was made. And x would represent the distance. So I might have, well, 30-yard kick, 0, it was missed. 40-yard kick, 1, it was made. So I'm going to have its distance, and then I will know whether or not it was a success or a failure. So then the probability of observing a 1 for y is going to be written as r pi I of x. So I will let us know for that specific observation of I, the probability of getting that success is going to be pi I of x. So then my logistic regression model will be written as the log, again remember, natural log, of pi I of x over 1 minus pi I of x is going to be alpha plus beta xi. And I is going to go from 1 up to our number of observations that we have. Now, a side note, just to sort of understand why maybe we discussed odds for a very, very long time, is if you look at the log of pi over 1 minus pi, and we think back to, well, what is this actually telling me? Well, this is the probability of success over the probability of failure, which isn't odds. So really we're taking the log odds when we're doing a logistic regression model. So this is where odds sort of are going to show up very easily for us. So as a warning, you're going to be seeing odds come back, not here for a little bit, but that's the reason why we talked about odds, is it's naturally going to show up in this logistic regression model. Now going back to actually looking at our model, so this assumes that the relationship between xi and pi I of x is this relationship. So then this model can be rewritten when I want to solve it in terms of pi instead. That pi I of x would be e to the alpha plus beta xi over 1 plus e to the alpha plus beta xi. And so what we need is we need a way to estimate alpha and beta, because alpha and beta, being Greek letters, are our population values. So our population kind of intercept, population kind of slope. And again, I said the kind of part because we're not technically doing a straight line relationship here. So how we find alpha and beta, there are multiple methods that some people may do. What we do in logistic regression is we use what's called maximum likelihood estimation. So maximum likelihood estimation is not the point of our course, but a real kind of quick explanation about it is it's really trying to find where your function will be maximized using a probability function. And so the idea is pretend for a moment that this is the function and that's what it looks like. It's trying to find that maximum of that function. And so it does it through what's called an iterative process. So it might start right here, and then it's going to look to the left and it's going to look to the right to figure out which way to go. So it can see here real quickly that if I go to the left, I'm going to get smaller, but if I go to the right, I'm going to get bigger. So let's take a step up. So maybe it goes to there, and then it's going to check. If I go to the left versus the right, what's going to happen? Oh, if I go to the right, it's going to get bigger. then it might go here. And then again, it's going to check to see. And then at some point, it's going to figure out exactly where to end at the exact maximum when there is nowhere to go that's going to be up. So that's the idea of what maximum likelihood is doing. So let's put this in context back to our example. So here we're trying to estimate the probability of a successful place kick. This is an actual data set from many years ago that we're going to use. So this data set has many different explanatory variables inside of it. I'm only going to be focusing on distance inside this data set, which is labeled as dist. The response variable is labeled as good 1 in the data set, where 1 means it was made and 0 means it was missed. So let's actually first look at this data set, just so you can see what it looks like. So you're given this data set so that you can make sure that R is working your way as well. So the only variables we're going to focus on are distance, and then if the kick was made or not. So those are going to be the only two variables that we are going to focus on here. We'll get to the others later. So before we dive into actually looking at this data set, what do you think should happen to the probability of making a place kick as distance increases? So distance is going to be our x. So as x gets bigger, what do you think will happen to the probability of making the kick? So I'm going to expect then pi of x more than likely to go down. Because for those that are not football fans, generally, it's more challenging to make longer kicks. So I would expect to see a negative relationship. So for our logistic regression model, we will be writing that as here. So my log of pi of x over 1 minus pi of x will just be alpha plus beta. And you can either put the x there if you want, or you could actually just put the word distance if you preferred instead. So you could actually just write it like that if you prefer. And for those that do write it the first way, so x would then be distance, and pi of x is the same thing here as our expected value of y, where y being equal to 1 means it was a successful kick, and 0 means it was failure. So we always want to know what we're modeling, because we're always going to be modeling the probability of success, and here we labeled 1 as being like it was a made kick up here. So it's always going to be modeling those ones that we use. So again, the main reason why we're using this generalized linear model, because we will talk about other generalized linear models, is because our response variable is binary or only has those two options, as it states here at the top of the next page for you. So here is some R code that we're going to talk through. A lot of this is also output, so I will make sure I show you my code here as we go. The first thing we're going to want to do, though, is get this data set into R. So first, if you go back and look at my data set here, it's a very big data set. It has lots and lots of kicks here inside of it. So I definitely do not want to have to somehow figure out how to manually enter this data into R. So the first way you see me doing it here, and this code will look a little bit different than in your notes because my folder directory was different on this computer, was to actually read in my table. I was using this read table. So kind of talking through that, the first one is my file directory. So let me kind of show you what that looks like here. So when I go to my E drive, the first folder I'm going to click here is NKU Teaching. And then this class is 327. So you'll see how that corresponds to these folders that you see here. My next folder I'm going to go to is my data folder. And then finally, that's where my data set actually is. So this is the name of my file. And I'm using a .csv. So that's going to be the one that you want to have as well. They're going to be also easier to read into R. Header equals true means that my first row basically consists of the names of my variables that I want. And how things are separated is by a comma. That's what a .csv is for a comma file. So that's why my separator is a comma there. And then the next thing I'm doing here is just having it spit out the first 3 observations. So this would be the first 3 rows. When I leave that comma, with it being open, it's going to give me all of the columns inside those first 3 rows. So I can see entirely what my first 3 lines of data look like, just to make sure that I read it in correctly. So that's if you want to read in the data. One benefit of using RStudio is we can also just import the data set. And I'm going to import it from CSV. Again, CSV files usually work a lot better in R. I can just browse to where I have that file saved instead. And sorry, things are not sorted by name, so let me just resort it that way so I can find it easier. All right, so there's my place kick data, and I want the CSV one, so click in that one. And this can kind of just show me a little preview of what my data looks like. And then I can hit import down here. And then it'll automatically bring it in here and kind of show me what that data set looks like. The difference is actually how things got read in here. The first time I did this, I actually named my data set place.kick. So that's why you'll see that's the name of the one up here. When I read in the file, it gave me placekick.mb. So if you wanted to change that when you actually import it, grab it here again to kind of show you how this works. So down here you could change the name of it if you don't want it read in with that like _MB. So if you wanted to, you could just recall it and just call it placekick, so you can name it there yourself if you want. Okay, so that's just getting the data set into R. All right, so that's all we've done there. Next, this was just me giving the data set when I imported it, when it had that _MB, and kind of naming it the same thing I had before. That way they were named the same thing, so it did not matter which way I read in my data. Now let's actually look at the actual code so you can see what the actual code looks like. So again, this mod.fit is just the name of what I'm calling it, so you can name that anything you want. I'm just calling it mod for model and .fit since I'm fitting the model. The function we are using here inside of R is this GLM function, and you'll see how everything kind of just popped up there, that it kind of shows you kind of the defaults of a lot of things and kind of what it's looking for. So one of the first things I have to give it, is my formula. So my formula is going to be good 1 is my y, and then the tilde is actually what separates our y from our x, so you have to use that tilde for this to work. And notice that I call it good 1 in dist because that is what these are called in my data set. So it's dist and good 1 are the names of those variables inside that data set. So I need to make sure that those match whatever they're called in my data set. The data I want it to use is in my place.kick. Now the family is kind of trying to figure out, in a sense, kind of what main distribution am I going to be using? So what kind of random component do I have to my generalized linear model? We're going to be using the binomial. The link function we're using is what's called the logit. There is more than one link function, which you will get to see later inside the set of notes as well. So that's the link function I'm going to use. This extra stuff of my NA_action.NA.exclude is if there's any missing data, it's going to say basically exclude that data. So if NA, so if anything shows up as not available, it's just going to exclude that data from being part of the model building process. This control is through that iterative process that we talked about. So with looking back here at my little picture of trying to understand this maximum likelihood process, kind of saying how many iterations of that are you wanting to go through. So I'm going to go through a maximum of 50 iterations. If it stops changing by less than 0.0001, it's going to go ahead and stop that process. Or going back to my picture here, if it's going to only go up by less than 0.0001 as it moves, it's just going to not bother moving, is that idea of what that's saying. Trace equals true. It means it's actually going to show me the process of how many iterations was done. The T is going to be the true. I want you to actually show it to me as it's going. So if all I do is run that line of code, this is the trace. It's kind of giving me this different types of things. So it's sort of showing me that number that it's trying to find. Here it's actually finding the minimum. That's not important to understand technically why it's the minimum here instead of the maximum. But it's basically telling me it only took 5 iterations before it stopped. It found a good fit, so it stopped. So that's the idea of what that's doing. Then the next thing I asked for is I wanted to find out what names are in this thing called mod.fit that I named it. So this is basically telling me what is stored inside mod.fit that I could ask for. So it gives me a list of all of these different things. Okay, let me kind of show you just that code being ran. So it spits out all those different things that I can basically be asking for as well. So if, for example, I ask for mod.fit $coefficients, it's going to give me an intercept and this thing called dist. So let's actually do that part. So what these values are for me. So let me go back here where I can actually draw on this for you. So this intercept that it's calling it, this is my estimate of alpha. And then this thing that it's labeling as dist, notice it's negative, is my estimate of beta. Okay. Going back up and labeling some more of this just in case you needed it. So this is my y. This is my x. This is our defining our random component link function that we actually want there as well. Another way I can actually get my estimates of alpha and beta is just to ask for a summary of this mod.fit. So summary is a function, so you can't change the name of it. Again, mod.fit because that's what I stored it into. So when I run that code, I'll give you a little bit more room to see. More of this at the same time. All right, so it calls the function. And then you'll see there are the same alpha hat and beta hat that we were given as well. So there's where those two values show up. What we also get, which are going to be very useful for us, is some p-values and z's as well. So again, let me go to where I can label this. a little bit better for you. Oh, did I not have that full thing written out? Oh, so apparently, sorry, I didn't put that in your notes here for you. So these are p-values that were being given there, and then just the z, standard normal, variables to be used for a hypothesis test given for you there as well. All right, so now that I've actually ran my model, we can actually write out our estimated probability function. So using that alpha hat and beta hat from my output, that's now going to tell me my estimated, that's why I'm putting a hat here on my pie, of x is going to be e to my alpha hat, which was 5.7818, minus 0.1145 times our distance, which was our x, over 1 plus RE to this value as well. So again, that's just using those values from our output, the alpha hat and the beta hat. So if I actually want to find for a 20-yard place kick, what is my probability of success? Well, I can just plug in 20 for x. So we would take e to the 5.7818 minus 0.1145 times 20 over 1 plus e to the same value, showing some math on what you should get for both the top and the bottom. So the bottom, remember, is just one bigger because it's just 1 plus the same thing that was on top. Gives me about 0.97045. So about a 97% chance of making a 20-yard place kick. If instead it was a 50-yard place kick, the same idea here, we're just going to be plugging in the 20 for x instead of the 20, plugging in 50 for x instead of the 20 that we had above. Which this time will give us much smaller numbers. Which gives us a tad bit more than a 50% chance here. As I mentioned, the z in the output gives us a z test statistic, which gives us a test for whether the parameter is 0 or not. This would help me figure out if distance is an important variable or not. So if I go back here and look at my p-value for distance, it is very, 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 very small. It's so small, it's smaller than e at negative 16 power. So basically it's a very, very small number. Remember, this idea means you move your decimal 16 places to the left of 2. So there's lots and lots and lots of zeros here in front of it. So this tells me then that distance is a very important variable to predict the probability of a place kick. Very much so. So that's the idea of trying to estimate the parameters and then use them to find estimated probabilities. So next week we'll dive in a little bit more of why the logit function, what other kind of link functions are there, how do I graph my probability function, and all of those types of things. But hopefully this week I want you to feel comfortable with the idea of why a generalized linear model, why we were probably using the logit link function for our success failure type data, and feeling comfortable with how to get data into R, as well as using R to estimate our alpha and beta. So please let me know if you have questions on any of that, as well as anything else that you're feeling uncomfortable with.